Okay, so let's look at this transfer function a little bit here, and just remember for the first order here, let's go back to the first order filter. Where we had my transfer function being a over s plus a, and then my cutoff frequency was simply equal to a. Well, now I don't have this, but notice here, I've got the same term here and the same term here. So your initial guess might be 1 over R1, R2, C1, C2 is equal to omega C. That might be your initial guess because it's kind of somewhat similar to that first order filter. But wait, we've got a second order filter here, so we have two poles. So we are close, but because we have two poles, we actually have, so this is wrong, but the actual answer is not that, it's not too far off. It's 1 over the square root of R1, R2, C1, C2. Which, if we wanted that in hertz, that would be 1 over 2 pi square root of R1, R2, C1, C2. Now, let's look at this thing here. If we let R be R1 and R2, so we're setting R1 to the same value of R2, and C being the same value as C1 and C2, we get omega C is equal to 1 over RC, and FC is equal to 1 over 2 pi RC. And with this, we also wind up with the transfer function being I'll say here, omega C squared is what's going to be on the top over S plus omega C quantity squared. Now that's if we let R1 equal R2. Now we also have to be careful though here. So this cutoff frequency is no longer the minus 3 dB point. But and that's where this terminology can get a little confusing, because we're saying, well, wait, the cutoff frequency is defined as the minus 3 dB point. Well, when we get into these higher order filters, we're still letting omega C being, quote, like this, what we'd call the cutoff frequency, but then we're actually really wanting to know what is my half power frequency, or the minus 3 dB. Now let's first see why it is no longer the 3 dB point. Well, let's go ahead and put in h at j omega here. So you have h at j omega, and we'll go ahead and put it at omega c here. Well, this would be equal to since these are squared here, I'm just going to write it as j omega c quantity squared over, I'm sorry, that is not right. We would wind up with omega c squared over j omega c plus omega c quantity squared. But let's think what we can do here. This is equal to omega c over j omega c plus omega c times omega c over j omega c plus omega c. Now, why would I write it like that? Well, the reason I'm writing it like that is because this is first order, and this is first order. So those are identical to my first order so words escaping right now. Those are the exact portions of my first order transfer functions. So I know, for instance, that this is going to be equal to 1 over the square root of 2 h max times 1 over the square root of 2 h max, if I'm looking at the magnitude of h at j omega c. I know that just because these are the first order responses sitting right here. When we set R1 equal to R2, these are just the first order responses sitting right there, so that's what I have to have. But then, if I look at this, and I like doing this just because it reminds us of some log properties. If I look at this in decibels, you're going to have 20 log of 1 over the square root of 2 h max, which is of course just 1, times 1 over the square root of 2 times h max. But let's look at a little bit of logarithm properties here. We know then, using log properties, that the magnitude of h at j omega c in decibels is equal to 20 log of 1 over the square root of 2 h max plus 20 log of 1 over the square root of 2 h max. That's just properties of logarithms. If you're multiplying things inside a logarithm, you can just add those logarithms instead. And then, of course, what did we just say here? H max is just 1, because these are passive filters. And then what do we get here? Well, this term here, we've already done this. It'd be 20 log of 1 over the square root of 2, which is minus 3 dB. And then this would be minus 3 dB. But what are we doing to those? We're adding those together. So we're getting here that at omega c equaling 1 over RC, we are at the minus 6 dB point. Okay, well, now we could extend this. So what I mean by extend this? Well, for a third order, as long as you let R equaling R1 equaling R2 equaling R3 and C equaling C1, C2, C3, that they're all equal, you would still wind up with omega c equaling 1 over RC. But now we are, but then this is a minus 9 dB point. And so then for a fourth order, we can continue on here, assuming that we let all the resistors be the same and capacitors be the same. We get omega c is 1 over RC, but this corresponds to the minus 12 dB point. So by just simply adding, because what we're doing here, let's look at the transfer function of what we're doing here. So the first order low pass, this is A over S plus A. This is first order. And then what we're doing is we're just increasing these A squared over S plus A squared. We're putting an additional pole. This is second order. H at S being A cubed over S plus A cubed. This is third order. And then A to the fourth over S plus A to the fourth would be fourth order. And we could continue on, making fifth, sixth, seventh, eighth order passive filters. But the key thing to remember is that this is a minus 3 dB point. This is a minus 6 dB point, minus 9 dB, minus 12 dB. So this creates a problem. We always want to design our filters around the minus 3 dB point. So that creates a problem for us. That is the problem that is easily solved. Because all we have to do here is say, okay, well, I've got my transfer function. Let's, for instance, look at a second order. And let's just go ahead and put some numbers in to make it a little bit easier here. So let's look at and say, well, we have an omega c. So we're going to look at a second order here. We're going to say omega c is equal to 1 kilorad per second, just for simplicity. So we would have my H at S would simply be 1, and I'm going to drop the kilorad for now, over 1 S plus 1 squared. We're just going to say this is in kilorads. You know, we're in kilorads there. So that's going to be my transfer function. Well, what do I want? Well, I'm wanting to know if I put H at j omega, and then this is equal to 1 over j omega plus 1 squared. What am I doing? I want to know, well, if I do this as a logarithm here, if I look at the magnitude of this, well, the magnitude of H at j omega would actually be relatively easy here. It actually turns out to be 1 over omega plus 1, I believe. Let me double check that. Omega squared plus 1. Because if we look at this as the magnitude of j omega plus 1 is the square root of omega squared plus 1. But then what are you doing to it? You're squaring it. And then I could go ahead and convert this to decimal if I wanted to, but really what I'm wanting here is I'm wanting this to be equal to 1 over the square root of 2. Okay, well, 1 over the square root of 2 equals 1 over omega squared plus 1. And so I'm going to solve this here. So I would have this being omega squared plus 1 is equal to the square root of 2 times 1. And then you'd have omega squared is equal to the square root of 2 times 1 minus 1, and then omega would be the square root of the square root of 2 times 1 minus 1. So let me go ahead and punch that into my calculator real quickly here. And if I did this correctly, we get 0.64, if you round it would be 0.644. But remember, this is in kilorads per second. So, we can figure out what that cutoff frequency is still, or not the cutoff, because we're defining this cutoff frequency to still just be 1 over RC, but we're finding my minus 3 dB point, or my half power point. But I don't want to have to do that for every single equation that I'm going to write. So I need to think about this a little bit more here. Okay, well, what did I do here? Well, I've got here, let's think about what we have here in this equation. What I have here, this is omega c squared, and so is this, omega c squared. Right? So if we kind of plug that through here, we'd have down here, this would be omega c squared minus omega c squared. Right? Because I'm just, everywhere I have a 1, essentially, that's my omega c squared. So really what I have here is omega is equal to the square root of omega c squared, square root of 2, minus omega c squared. Which, wait, there's an omega c squared in both of those, so you could factor it out. And we'd wind up with a square root of 2 minus 1. Now, if we wanted this in frequency, all you do is divide both sides by divide both sides by 2 pi. So this gives me my 3 dB point for second order. Okay, well that's great. But now what if I want to do third order or fourth order? Well, let's go back again to where we were doing things here. Well, if we're doing third order and fourth order and everything else like that, what we'd have here is we'd be actually getting different powers of this here as far as taking the square root of it here. So doing a little bit of algebra, I'm going to skip it, but what you wind up with here is a general equation, and this is the important ones from this here, is that my 3 dB point is going to be omega c times the square root of 2 to the 1 over n power minus 1, where n is the order. So instead of doing a square root, we'd do a cube root. Instead of doing a cube root, you'd do a fourth root, so on and so on, depending on the order of the filter. And of course, you could write this as f at 3 dB is simply equal to fc square root of 2 to the 1 over n minus 1. Now, I know these last two lessons have been a little long here, but I wanted to get through all the theory in 2 lessons so we can look at some analysis and design examples in the next lessons.